Okay, so you'll be happy to hear that we've arrived at the last topic of the course, and maybe what's going to be the last video. It depends on how long this takes. And these are applications of the definite integral, some of which I think are pretty cool. I'll be able to try to explain them as best as I can, given that we didn't go into a lot of the theory of the definite integral in tremendous detail. And so some of the formulas might seem a little weird without kind of a deeper discussion of what the integral is really doing. Anyhow, the first topic, so there are four applications I want to discuss, and there are two applications from economics and two kind of that can be applied in different contexts, including economics, but also like population and so forth. So the first topic is the average value of a function. Okay, so we all know how to take, and we know how to take the average of two numbers, right? Of two numbers, right? So if you have, say, like the average of 5 and 10, sorry, the average of 5 and 15 is 10, and the way you compute that is you have 5 plus 15 over 2 is 20 over 2, which is 10. So I put that there, right? And this can be done, and so we can also, I mean, similarly, we could take the average of n numbers. So we'd have, like, say, I don't know, x1 plus x2 plus xn over n, and that would be the average of the numbers x1 through to xn. And I won't do too many more examples because this is not the kind of average we're going to be doing, but it illustrates kind of what the idea is. So we can also consider the average values of a function f, or the average value of a function f of y equals f at x at a set of n numbers. So, and this average would be very similar to the one above, is computed by the formula fx1 plus fxn. Let me just clean that up a bit. Fx1 plus fxn divided by n. Okay, so this is the kind of thing, you know, if you're dealing with some amount of, just like a large amount of data, but you have a finite collection of data, you might want to figure out what the average is. So, for example, like if I'm looking at your test grades, right, I compute this kind of an average. I, take all the, or the, I don't compute it, Pearson computes it for me, or Excel, depending on what I'm using. I would just take all the grades, add them together, and divide by the number of students. And this kind of average would be if I have some function I'm studying, where I want to understand the average value, or the average kind of size of the function at the points. So this could be, for example, if I wanted to understand, what would be a good example of something like this? Say I have, like, I'm going to a store and there are n items that I want to purchase, and I want to figure out what the average price is on those items. I could compute this kind of a thing, right? But that's not what we're going to be doing in this class. What we're going to be doing has to do with averages of an infinite set of numbers. Like so this is how you average a finite set of numbers, a finite set of points. How do you average an infinite set of numbers? So, and this is not so obvious. So question, how do we average an infinite set of numbers? Collection of numbers. Like, for example, I could ask the following question. We could ask ourselves, like, what is the average population in the US over the last 5 years? Now, there's a number of ways you could do this, right? There's a number of ways you could, I mean, you could say, okay, the population at the end of the first year was 330 million. The end of the second year is 332 million. And the end of the third year is 336 million, et cetera. And then you could compute this kind of an average where your N would be 5. But that's not very accurate because population is continuously changing, right? I mean, population isn't just, given by a discrete set of points that, the population might be one thing in January, another thing in February, one thing today, one thing tomorrow. So it's changing continuously. It's not just like snapshots at the end of each year. That doesn't give you a good idea. That doesn't give you a good approximation of what the actual population, how the actual population is evolving, right? So the population may be given by a function like e to the 0.02t, some kind of exponential growth, just for an example. And then you want to say, you want to average, we would want to average this function over the interval, like t starting with 0, like from t equals 0 to t equals 5. So it's like you're averaging not just like the population 5 points at the end of each year, but you're averaging it continuously and putting all the information into the average of the continual change in population growth. That's a much more accurate picture, much more accurate average or meaningful average than you would have by just picking the population at the end of every year and then averaging those 5 numbers. Because like I was saying, the population is continuously changing. We want an average that reflects a continuous increase, in this case, in the population that captures the change, the continuous change that's happening. Okay, so this is not there's no obvious solution to this, right? Because we don't have a mechanism for adding together, for adding together infinitely many numbers. We don't know how to do that in an obvious way. So this problem is solved by the integral. So in some sense, like I said this at the very, very beginning when we talked about integrals, we were talking about the definite integral, that this integral sign, so the indefinite integral, that the integral sign, that squiggly s, is really for sum. So one way of thinking about the integral is it's a continuous sum. And we didn't really talk about this idea very much in this class, but if you take a more theoretical class, that's actually how you start to think of the integral. The first thing you kind of say. Okay, so the problem with this, trying to figure this out, so problem, it's not clear how to add together a continuous set of items continuous set of numbers. I'm still thinking about getting things to the store. Sorry, a continuous set of numbers to find an average. And the answer, the integral provides us a tool to do this. to do this. Okay, so I'll make the definition. So let f of x be a continuous function on the interval x x equals a to x equals b with, okay, so with, I mean, when I say this, a is less than or equal to b. I see strictly less than b. Then the average value of the function f of x on this interval is the quantity integral from a to b fx. Let me clean this up a bit. Fx dx divided by the length of the interval b minus a. So this is f average, average value on that interval. So I should say on the closed interval AB, right? Okay, so the way I think about this, so my intuition for this is that AB fx dx is a kind of continuous infinite sum. And then we are dividing this sum by the length of the interval, which kind of plays the role of the number of the, the size, the number of your sample. Like when we were averaging n numbers, if I'm averaging all your grades, there's 20 students in the class or 30 students in the class, what have you, add 30 numbers together and I divide by 30. Now I have a continuous set of numbers so that the size of the data is like the length of the interval is replaced by the length of the interval, by the length of the interval. Which sort of acts like the size of our data set. Okay, so that's kind of like my intuition. So that I think of this as being like this quantity integral from a to b fx dx, b minus a, as being like continuous version of the formula that I talked about above, where you have like fx1 plus fx2 plus fxn. Okay, so that's kind of what that's how I view it intuitively. Okay, but we need to figure out how to use this. We need to do some examples. So let me just have a sip of water. And if you ever study integration some more, you'll kind of really understand in a precise way why this average formula is like the integral is the right thing to replace the finite sum. But leave that for now. On the other hand, and I'm sorry if this is a bit of a diversion. On the other hand, I didn't want to I don't know, I got really sick of just throwing formulas at you without any kind of motivation, because then to me it just sounds like, like if I just see formulas without motivation, a lot of the times it just seems like gobbledygook, and I don't really enjoy thinking about it. But especially when maybe there isn't a clearly obvious use for it, but we'll see a use for the average formula in a second. But so I'll start off with an abstract example, and then I'll do a application, like something with involving population that we talked about earlier. Okay, so here's the first example. So find the average value of the function f at x equals 1 minus x from x going to -1 to x equals 1. So on the interval, in other words, on the interval -1 to 1. Okay, so this is a straight application of this formula here. And so let's just give it a whirl since we're experts at definite integrals now. Okay, so f average on this interval is going to be integral from -1 to 1. What was our guy? 1 minus x dx divided by 1 minus -1. So divided by the length of the interval, which is 2. So right endpoint minus left endpoint. This isn't too bad. So f average is equal to -1, 1 minus x dx divided by 2. And, I'll put this out as a 1/2 out in front. I mean, it looks a little bit better. Cat, you cannot solve this problem. Yes, I know you're lonely right now, but you just sit there and have a nap. Sorry about this. There's a cat here. It's actually the other cat. Okay, so we can just find this integral. We got to find any derivative, any derivative of 1 minus x, and or we can split it up if you like. We've been doing that, so maybe I'll do that before I find the antiderivative. See what we get: -1, 1 dx minus integral from 1, 1 x dx, and multiply everything by 1/2. And now we're good to go. So any derivative of 1 is just x. We evaluate at 1, subtract the result by evaluating at -1. So that's that bar notation that you love. And we have x squared over 2 is the antiderivative of x, is an antiderivative of x at 1, and then evaluate it, at -1 and subtract. Okay, so we just got to do this. So what do we get? So we get 1/2, 1 minus -1, minus, now watch your parentheses here, right? 1 squared is 1, so it's 1/2, but -1 squared is also 1, so you actually get 1/2 minus 1/2. And so that cancels. And what you're going to get in the end of the day is 1/2 times 2, so the average value is 1. And this is, okay, so this is an integral calculation, right? But we should kind of maybe take a quick look-see and see if this corresponds to our intuition. So we're done the question. We found the average value, but let's think about, does this correspond to our intuition? Question mark. And so let me draw the graph. So I've had to move the iPad to avoid Kat, who was about to finish the question for me. So we have -1, say, is here. We have 1 is here, right? So this is maybe not to scale, but this is the line. So just drawing the line of y equals 1 minus x. Right, that's a line of slope -1 with y-intercept 1. So this is 1. It's not, like I said, not to scale. So maybe I should, we'll leave it for now. But you can kind of see why, like, 1 would be the average of this function on the interval. At the left endpoint, the function has value 2, right? And at the right endpoint, at 1, the function has value 0, right? So 1, this value 1, this average value we found, is right smack dab in the middle of the two extreme values of the function on that interval. And so that's what we should expect for an average. So it tells us that this formula is doing the right thing in a case where we can actually draw the picture and to understand intuitively what's going on. So yes, the value 1 is right in the middle, is the midpoint, is right in the middle of the values at the endpoints of the interval, values of f at x at the endpoints of the interval. In fact, so it is the average of the values at the endpoints. So in this case, I mean, the average value of the function is the average of 2 and 0. It is literally the average of the value at the endpoints. That is not always true, but because we have a linear function, that actually happens to be true in this case. But I won't go further down that road. But it just shows you that this formula does what it expects you to do in a very, very easy case. Okay, so let's do an application. Example of an application. What I was hinting at earlier. Okay, so this is example 2. So assume that a country's population is now 3 million and is growing exponentially with a growth constant or a growth rate, I think we're using the word growth rate, of 0.02. And then this is exactly the question I was asking to motivate this whole thing. What will be the population of the country in 5 years? Question mark. Okay, so you have a country, population is growing exponentially. You want to compute what is, so not what will be the population, sorry. What will be the average? What is the average of the population during the next, actually not just 50 years. What will be the average, the average of the population of the country over the next 50 years. Okay, sorry, said it correctly now. So your population of the country is continuously growing at an exponential rate, right? And we want to figure out over the next 50 years period, what would be the average of that country's population. And I said you could take every at the end of every year for 50 years, you can measure the population and average together 50 numbers, but that's not an very accurate average because it doesn't capture the fact that the population is continuously changing, right? And it's changing from not just from day to day, from minute to minute, second to second. So you want to somehow incorporate the fact that there's an infinite measurements, continuous measurements. You have an infinite continuous data set of population when you compute that average to get a more representative average, right? That you're not just seeing some anomalous point in the data when you select only a few points. Right, okay, so first of all, we're not given the function here, right? So we got to remember how to translate this English into math. So country's population starts out at 3 million and is growing exponentially with a growth rate of 0.002. So we have to put this put this information into a function by remembering what our knowledge of exponential growth. So recall, right, exponential growth so I'll just say P of t for population is equal to C e to the kt, where C is the initial size and K is the growth rate. Right, so in our case, in our example, we would have C was 3 million, so I'll keep it in millions, so I don't want to have to write like all these zeros. And we're told the growth rate was 0.02. Okay? So the function that we have to average, right, is this exponential growth function. So we want to average this function from t equals 0 to t equals 50. Okay, so we're going to use the formula that we developed. It's gone up into the stratosphere now. That we developed up here, right? This puppy, right? Where a is 0, b is 50, and the fx is our exponential growth function, but the variable here is t instead of x. But that's not a big deal. Okay. So using the definition of average value, we have the average, so the population p average would be, okay, so 1 over 50, the length of the time span, the integral from 0 to 50, p of t dt. And so this is 1 over 50, the integral from 0 to 50, 3 e to the 0.02 t, and dt. Okay, and so we can pull out the 3. We know how to do this, right? And we're left with the figuring out the integral, the definite integral of e to the 0.02 t dt. So we remember this all important. So recall this all important integral formula that an antiderivative, the general antiderivative of e to the kt is e to the kt over k plus c. So that's what we need to use to compute this definite integral, right? Because we need to find an antiderivative and then just evaluate it at 5 and then subtract what we get when we evaluate 0. And we did this in a previous video. But to find the antiderivative, we need to remember this formula, right? So, and we could say, okay, this is the antiderivative of e to the 0.02 t is e to the 0.02 t divided by 0.02 between 0 and 5. And remember, when we're doing the definite integral, we use any antiderivative, a particular one. The plus c doesn't matter. We don't need it. If you put it in, it'll cancel out. So don't make more work for yourself by putting it in. So this is 3 over 50 e to the 0.02 times 5 divided by 0.02 minus, now you have to put in that 0. Remember, this is e to the 0 is 1. So the numerator becomes 1. And then you just divide by 0.02. And, oh, sorry, this is not, I wrote a 5 here. This should have been a 50. 50. Okay, sorry about that. Drop to 0 on the upper limit there is all fixed. Okay, now 0.02 is actually 1/50th. So 0.02 is actually 1 over 50. It's twice of 1/100th. So there's a lot of cancellation that happens here. Let me get this straight. So this is 50 times 1 over 50. That these actually cancel. And then the 3 is left alone. So you get 3. This is 1/50th times 50, you just get 1. So e to the 1 minus 1. And so this is 3 times e to the e minus 1. And if you want, you're talking about population, so you probably want some kind of estimate that's, you want a decimal estimate to give you some sense of what the hell this means. And so this is approximately 5.5 0.1548. And remember, working in millions, so this is million. Okay, so in other words, what is this saying? So this says that over this 50-year period, the country has an average population of 5.1548 million. And that's a very accurate, no, it's the most accurate average you can come up with, right? So hopefully you believe towards the end of this that this is somewhat a natural thing to look at, this average value. Okay, so that's the end of our first application of the integral. The next application, so application 2, I think we'll only have time to do 2 applications in this video, and I'll have to save the economics applications for another video, which is okay. They're kind of like their own stuff anyway. So as computing volumes of solids of revolution. Okay, so what does this mean? So in general, it's like pretty tricky to compute a volume of something. Like you learn in school that like the volume of a sphere of radius r is 4/3 pi r cubed, but like where the heck does that come from? The Greeks knew this for some very deep reasons, but actually you can prove that using this theory of calculus. We won't do the sphere, it's a little bit hard, but let me just give you an idea of how you could get a sphere in this way. So what is a solid of revolution? So a solid of revolution is taken by, you take some curve, some function, y equals gx, right? You think of it as giving you some area, like this case, like an area of a semicircle, and you take that area, and what you do with it is you rotate it about the x-axis, right? You rotate it about the x-axis. I mean, it comes out of the page. You think you're taking a semicircle, rotating it about the x-axis, and back, about into the page, and then back out again, in 360 degrees. You're going to get a sphere. So if this is if this is radius r, so this is minus r and r, and if we rotate the area under a semicircle of radius r, as depicted above, about the x-axis, it will give us, it will produce a sphere of radius r. So kind of play with it a bit in your head. You can even, it's kind of tricky to do this with a piece of paper, but think of like taking something like this. Sharpie is not a semicircle, but you rotate it around, you get some kind of a cylinder, right? If you rotate the region in the Sharpie around the x-axis, you cut out a cylinder, right? So the question is, how do we compute the volume? So suppose you don't know the formula for the volume of a sphere. So we can use calculus, we can use integral calculus to compute the volume of the sphere obtained in this, of radius r. So integral calculus tells us, gives us a way of computing the volume of a sphere of radius r, which we know what the answer is. Okay, so here's what I'll tell you what the general formula is, and I won't the example of the. Yeah, we could do, the example of the sphere is a little more complicated than what you'd have to do in the homework. I'm more than happy to show you how to do it in the live section, but I won't work it out in the video because it involves like a little bit more symbols and more complicated functions than you'd have to deal with in the homework. But it will give you the classical formula. Okay, so and this is this. So this procedure is volumes of solids of revolution. So this sphere is called a solid of revolution because we can get it from rotating a semicircle about the axis, right? And other solids of revolution. Okay, so I'll tell you the general formula. And again, this formula is kind of very hard for me to justify without doing a lot more geometry. But again, I'm happy to explain it to you in the live meeting, but it would take me an entire video just to explain where you get the formula from, or at least almost an entire video. In general, if y equals g at x is a continuous curve function from x equals to a to x equals to b, we can compute the volume of the solid of revolution generated by rotating the area under g at x from x equals a to x equals b via the following formula. Again, where this formula comes from, I can explain it if you like. It's not that easy. So the volume V is of the solid of revolution a to b is the integral from a to b pi times the value of the function squared dx times dx. So that integral. So it's this integral. And if you just draw a picture, if I draw a picture for you, the general situation is you might have like your function gx might look like this, just another thing that's not a circle. So here's your x equals a, say, and go here. X equals b. And you take this region and rotate it, right? You'll get some kind of a funnel-like thing. I mean, it'd be hard for me to draw, but right, you can imagine rotating this region, you would get something that kind of looks like a funnel with hyperbolic edges. Okay, and so this formula gives you the volume of that funnel, right? Okay, so in the example, so to obtain the volume of a sphere of radius r in this way, is capital R in this way, right? You let g at x be the square root of r squared minus x squared, and a equals minus r and b equals capital R. And if you do that, I claim if you do that and you compute this integral, from minus r to r, that you get exactly 4/3 pi r cubed. Okay, but I'll let you do that. Or I can do it in a live meeting. But we will do something easier, okay, than this. This is a little trickier than what I want to do. I mean, we can do it. You have the tools to do it. It's possible. But I will focus on something a bit easier. So we will do an easier example. Okay, so find the volume of the solid of revolution generated by revolving the region under the curve g at x equals 2x minus x squared from x equals 0 to x equals 2 about the x-axis. Okay. Now you can draw the picture if you're interested. I mean, it looks something like, what does this look like? It's a little tricky. I mean, the picture's a little bit maybe not super helpful here. We don't need it. It's not a shape you'd recognize. So we can just kind of go with the formula, right? Which is, where did it go? There it is. Right, we got to compute this integral. Our a is 0, our b is 2. So the volume of the solid is given by the definite integral. So 0 to 2 pi, I'll put the pi outside, save us some time, gx squared dx. So this is pi 0 to 2. The g was this guy, 2x minus x squared. And we square it. Now you have to square it. So the trickiest thing, I think, about doing these integrals is that to be able to solve the integral, you have to expand this. You have to FOIL this out, right? And write it in terms of sums of powers of x, powers of x's, so we can use our sum rule and the known reversing the power rule formula. You can't just immediately find an antiderivative from this. It's too tricky. So to solve the integral, we have to expand the quantity 2x minus x squared squared. So what do we get? So we get the volume is pi times the interval from 0 to 2, 4x squared minus 4x cubed plus x to the fourth dx. And now we can use our sum rule, etc. I'm going to skip that step because eventually you get to the point where you can do these two steps interchangeably. I can recognize, okay, I need to compute a difference of, or sum or difference of different antiderivatives. I can write it out loud in terms of the integral, or I can just kind of do it in my head and then just do it all at once. So first I compute the antiderivative of 4x squared, which is 4 times the antiderivative of x squared. So it's 4x cubed over 3. And this one is 4x to the fourth over 4. And so this guy here is the antiderivative of x to the fourth, which is x to the 5 over 5. And all of this jazz is evaluated 2 and then subtract the result at 0. And so this is kind of annoying. You need a calculator, but this is 4 times 2 cubed is 8 over 3. The 4's here actually cancel. And you get 2 to the 4th is 16. And then you get 2 to the 5th is 32 over 5. And then the bottom limit turns out to be 0. So what you get here is pi 32 over 3. Sorry, let me write that better. 32 over 3 minus 16 plus 32 over 5. And if you add together these fractions, you can do this on your calculator if you wanted. It's 16 over 15. So the volume, and usually you want to write the pi on the other side, is 16 over 15 pi. So that's the volume that we end up with for this weird shape given by like basically rotating this funny parabola about the x-axis. I mean, that's the kind of, it's not a shape you would, like I said, you would think about, but it's the kind of question you might see on the homework. Okay, so I think I'll end the video here. We have 2 more applications to do, and these are applications from economics. So they're kind of their own thing. They won't take as long as this stuff because I can kind of explain a little bit about how they work, but they're actually fairly, I can't go into a lot of detail, and they're not very, they're not as involved as these kind of 2 examples here that we've done. All right, folks, thanks for tuning in. Just one more video to go.